Welcome one, welcome all. Today we will discuss the first chapter in our textbook. It is on classification of materials. Let's get started. This is our first lecture for our Properties of Engineering Materials course. Over the course of the semester, we will introduce fundamental concepts in material science engineering. We will examine how the internal structure of materials affects the material properties. We will also examine how the processing of materials changes its structure and properties. Through the above, we will explore how to tailor the material properties to the desired engineering task. By the end of this semester, we hope that you will be better able to select appropriate materials for an application design. Why study material science? What is material science engineering? Since the mid-20th century, the term that has been adopted for the branch of engineering concerned with materials is material science and engineering. It is a blend of fundamental science and of practical engineering. There is significant overlap with many other fields, including metallurgy, ceramic engineering, biology, organic and physical chemistry, and condensed matter physics, just to name a few. How does material science benefit you and society? Over the course of human history, material possessions have served many roles. In the earliest societies, they likely served as both tools and weapons. Today, they serve to increase quality of life in many different ways, including transportation, communication, shelter, information, and numerous other means. To underscore this, we still define eras in human civilization in terms of materials. The Stone Age dates back as far as 2.5 million years ago, when our human ancestors shaped stone tools. Much later in the Stone Age, flint and pottery emerged. During the Bronze Age, from roughly 2000 BC to 1000 BC, metallurgy begins to emerge, and alloys of copper and tin were utilized to make improved weapons and tools. Alloys are metals composed of more than one element. The Iron Age spans from 1000 BC to about 1 BC. During this period, iron alloys replaced bronze for tool and weapon making. How will history describe our era? Perhaps by our use of silicon in electronic devices, or perhaps by the polymers that have become so ubiquitous in our lives. Based upon chemical composition and atomic structure, we group solid materials into one of three basic categories: metals, ceramics, and polymers. Metals are composed of one or more metallic elements and often small amounts of non-metallic elements. Atoms in metals are arranged in very ordered fashion and are comparatively dense. As we shall see, metals are strong and can be readily formed into practical shapes. They tend to be ductile, meaning that they can be greatly deformed without fracture. They are also good thermal and electrical conductors. Ceramics are compounds between metallic and non-metallic elements, commonly oxides, nitrides, and carbides. Common examples include aluminum oxide, silicon dioxide, silicon carbide, silicon nitride, porcelain, cement, and glass. They are stiff and strong. Most conventional ceramics are brittle, however. Brittle is the opposite of ductile. They also tend to be poor conductors of heat or electricity. Polymers are often organic compounds that are chemically based on carbon, hydrogen, and other nonmetallic elements. Common polymers include the ubiquitous plastic and rubber materials found throughout your homes. Polymers usually are large molecular structures with a chain-like pattern. Polymers are ductile. They tend to lack strength and stiffness comparatively. They are also poor conductors of heat and electricity. They often tend to have poor thermal properties. They are not ferromagnetic. We will expand upon this list slightly to include composites, which combine two or more of the above to achieve properties that neither possesses. We will also sometimes speak of glasses as separate from ceramics due to how useful they have proven to be. Similarly, we will also spend a fair bit of time discussing semiconductors, as they too have had a remarkable impact on society. One area of recent growth in material science is biomaterials. As improvements in nutrition, medicine, and engineering have led to increased lifespans, new needs have emerged. With age, or with certain illnesses, joints may deteriorate. The hip joint carries a great deal of weight, and failures of the hip are becoming more commonplace. Roughly 250,000 people each year require a hip implant or replacement. In the image to the right, you see a deterioration in the hip joint. What considerations would we need to keep in mind as we design a hip implant? Well, it should have good mechanical strength, capable of carrying significant loads, and capable of having the load applied and removed many times. As it is a joint, good lubricity is essential as it needs to rotate. Finally, it needs biocompatibility. Neither of the above considerations will matter if the body rejects the implant. Here, we see how the hip implant works. There is a ball within a cup. The cup is affixed to the pelvis. The stem of the implant is affixed to the femur. Here we see a representative device broken into components. Design process is an essential part of engineering and can be useful even outside of your engineering life. The material selection process is briefly outlined here. First, decide upon what the application or task is. Consider what material properties are required or essential to carry out the task? What material properties would be desirable for the task? Next, identify materials that possess these properties. And finally, consider the processing required to make the material suitable to the application or task. Metals have high thermal and electrical conductivity because valence electrons are free to roam. Metals tend to be stiff, strong, ductile, and have high thermal and electrical conductivity. Polymers and plastics tend to be flexible, ductile, much lower in strength, low density, and tend to be thermally and electrically insulating. Ceramics tend to be stiff, strong under compression, but brittle. Ceramics are thermal and electrical insulators. Here, we see a tungsten metal filament that will carry a current and become warm enough to emit light. Here, we see a polymer seal that serves to electrically isolate one part of the bulb casing from another part. Here, we see a porcelain ceramic serving to thermally and electrically insulate. The filament is housed protected behind a transparent glass. As an exercise, apply the material selection process for various bicycle components. Write out a simple table and match the essential and desirable properties to the application or task. Identify the material or materials that might be suitable. And finally, identify the processing that would be required. The list of properties is 1. Transparent and waterproof, 2. Stiff and ductile, 3. Rubbery and tough, and 4. Thermally stable, electrical conductor. The list of materials is 1. Tungsten, 2. 80% silicon dioxide plus 20% sodium oxide, 3. Polybutadiene rubber, and 4. 1020 steel. The list of processing techniques is vulcanization, float on molten tin and cut, C. Wire drawing, and D. Extrusion. Likely the list of processing techniques included some unfamiliar terms. Let's define them. Drawing is the process of pulling material through a reducing die with tensile force applied to the material. Extrusion is pushing a material through a die orifice with compressive force so it emerges with reduced cross-section in the shape of the die opening. Vulcanization cures a sticky mass of raw rubber with sulfur and heat in a mold to give improved mechanical properties. Float on molten tin. Floating material on molten tin in a liquid state to maintain a uniform thickness of material. With that in mind, now I would ask you to go back to the prior slide and try to complete the exercise. Please let me know if you have any questions. We will discuss many topics over the course of the semester, so a good breakdown of the topics is as follows: bonding, crystals and defects, mechanical properties, deforming and strengthening metals, phase diagrams, non-equilibrium microstructures, polymers, electrical, and possibly magnetic and optical properties, ceramics, and composite materials. Here is what I hope that you take away from today's lecture and from the first chapter reading. We can identify important materials, families, and properties. 2. We know the role of materials selection in the engineering design process. For a new problem, we can go from design requirements to material selection. And 4, we can relate a material's type to its properties to processing. Okay, that's all for today. As always, you are all awesome. Have wonderful days. Thank you for stopping by. Don't be strangers. Enjoy your days, but not so much that I don't see you next time.